Hello everyone. So all this while we have been talking about traction, and we have focused in the last few lecture parts on the stress tensor and the various components of the stress tensor. Today we are going to start an entirely new topic on the normal and the shear components, not of the stress tensor but of the traction vector itself. So and in the process we'll also see what is the connection with the stress tensor. So in order to keep things general, what we'll do is we'll take a general plane like this. So we'll take a general plane which is like this. Please note that this is not a three-dimensional body. So whenever I draw an arbitrary shape, or whenever I had drawn an arbitrary shape till now, I had meant it to be a general three-dimensional body. This is not a three-dimensional body, this is a general plane. Now the unit outward normal to it would be drawn somewhat like this. So this is the unit outward normal to it. Let's say this is the n hat, and the traction vector originating from this point itself, let that be like this. Okay, now I would like to highlight at this point, in case you haven't realized it yourself by now, is that the traction vector, this is the traction vector, this need not in general be parallel to the unit outward normal. I am sure most of you have realized it by yourself by now. So we draw it in a different direction. Now what we say for the normal component of the traction vector is simply that you just take the component of this vector along this unit normal. So usually you take components of a vector along along the coordinate axis directions, and we can have coordinate axis directions set up in this fashion. So let's say our coordinate axes are set up like this. Let's say this is x1, x2, x3, but we do not wish to take the components of this traction vector along this x1, x2 or x3. What we wish to do is we wish to take the component of this traction vector along this unit outward normal to this plane, which is n hat. Okay, so the way that is denoted is T superscript capital N, that is the representation we'll use, and you understand that will be simply the traction vector dotted with the unit outward normal. As simple as that. Okay, so that is all there is to the normal component of traction vector. So this is what we refer to as the normal component of the traction vector, or of T. So what about the shear component? Now the moment we say shear, our visual understanding will tell us that it must be some component of the traction vector which is grazing along this surface, which is lying along this surface. It's like grazing along that surface, okay, shearing along that surface. Now if this is the unit outward normal, then this traction vector has a unique component along this direction, which is represented by this T superscript capital N. But the shear component, it is not unique, because you can take the component of this traction vector along this direction, and when I say this direction, I mean a direction which is like this, but lying along the plane itself, or it could be along this direction, it could be along this direction, it could be all around this point but lying on that plane. So which is the shear component that we are talking about? Are we talking about all of them? At this point, no. We are talking about a very specific, a very particular kind of shear component of the traction vector. So which one? So you see, no matter which way you draw this traction vector, because you have two vectors here, they will be lying on a single plane. Okay, I am not talking about this plane. Sorry about that. I am not talking about this plane. Okay, I am talking about the plane on which both this n hat and the t vector will lie. So please remember your vector mathematics from your high school. So we can understand that there will be some plane like this, which will be containing both the n hat and the t vector. Now, staying within this plane, you can understand that there is only a single direction, which is this direction, along which you can take the component of this, and that is the shear component we are talking about. Okay, so what we'll say is that the diagram is actually quite it has come out to be nice, because this part lying on that plane, that itself is the shear component we are talking about, and this thing, okay, so let me just thicken this unit outward normal a little bit. It will be still visible. So this is my unit outward normal, and the yellow vector component here, this one, that is my Tn, and this here, that is my Ts. Okay, so how do I represent Ts? So you understand that so let's say we use this color. Okay, so this will be some Es vector. The Ts will be equal to T vector dot Es. Now you can take it as a little exercise to represent Es hat as some combination. Okay, so what is the representation of Es in terms of the T vector and the n hat? Because when you were given the situation, you only know about the T vector, which you are concerned with, and the unit outward normal, which defines this plane. So you only know these two things. So my question is, how do you connect these two? Okay, so this is just a simple exercise in vector mathematics. I'm sure you can figure it out. I will not spend any time doing this. So the hint is that you have to take some cross products. Okay, now what is interesting to note is how does this representation turn out if we use the Cauchy's formula or the Cauchy's relation or the Cauchy's stress theorem. So just to recapitulate, if we go back a few slides, it is present here also. So this thing, this basically came from the Cauchy's stress formula. So if we go back even more, so this is the original place where we talked about the Cauchy's formula or the Cauchy's law or relation or stress theorem, and utilizing the symmetricity of the stress tensor, we could write it like this. So what happens if we write this, if we use this in our current form of the Tn? So let me utilize this space here. So Tn is equal to T vector dotted with n hat. So that is in terms of the stress tensor, mind you. So like this. So this is the stress tensor dotted with the n hat, this entire thing dotted with the n hat. Okay, so what is the equivalent matrix representation of this normal component of the traction vector? So it's very useful to write it out, because this is something, this matrix representation is something which you can actually input directly into some kind of a computer system like MATLAB or Python, and then easily calculate the actual value of this Tn. So what we can do is, for the equivalent matrix representation, we can write it like so T vector dotted with the n. So this thing, this entire matrix representation would be T vector transpose. So please note that this is a little bit of a confusion here. I am using the symbol T for the transpose, okay, but I hope it will be clear. Okay, so what I'm basically using here is that if you have A vector dotted with B vector, the equivalent matrix representation of it is A vector transpose B vector. Okay, it is very important to use this transpose, otherwise you'll have a mismatch in the way the matrix multiplication has to be carried out. Okay, I'll erase this part. Now the T vector itself, that is the sigma transpose dotted with n. So the transpose of this, okay, so this will be sigma transpose n hat transpose of this entire thing, because this transpose is coming from here, n hat. And finally what we'll have is, so this is like A B transpose, so that will be B transpose A transpose, so that will be ultimately N transpose So if we go to the next slide, we can quickly summarize what we have just found, that Tn is equal to this one, sigma transpose dotted with n. So this is the compact notation, and that dotted with n hat, and this entire thing is equivalent to, in matrix representation, to this thing. So I missed the transpose here, because this is a sigma transpose n, entire thing transpose, so this should be n transpose sigma n. So I believe it will be clear to all of you here. So this is N transpose sigma N. You also note that we have this relation to be true. So Ts square, that should be equal to T vector, take the magnitude of that, square that, and then Tn square. So basically what we are doing is we are utilizing the fact that the Tn, the Ts and the T vector geometrically they make up the right angle triangle. So basically we are using Pythagoras' theorem to write this as Ts square plus Tn square is equal to magnitude of the T vector square. That's what I have written here. You also note that the following must be true, that the T vector is simply equal to the Tn n hat plus Ts. So this is very simple to understand. So I'm just writing some basic truths in front of you. Furthermore, another very useful relation to note is the Ts written in terms of the stress component. So Ts we have already seen is equal to T vector dotted with Es. Now the equivalent matrix representation, let's write it here, would be T vector transpose Es vector, and that is equal to, just like before, sigma transpose dotted with n hat, the entire thing transpose Es, and that n hat, the matrix representation of that transpose, sigma tensor Es hat. Okay, so please note the similarity of this particular form that I have just written with this form. Okay, so the first two parts, they are the same. It is only in the last part where the difference is, and that is of course coming from the fact that this is along the normal component and this is the shear component. Okay, now all this while we have been talking about the Es vector, the very particular shear direction. What about another shear direction? So suppose we do not limit ourselves to be lying within this plane that is that contains the T vector and the n hat. Suppose we are no longer restricted to this particular plane, then we can very well have a direction somewhat like this, some general direction like this, which is of course lying again on that plane, and let's say we call that as the unit vector along that to be Et. So no problem, we can have a component along that direction just like this. All that you have to do is take the traction vector dotted with the Et vector. Of course we have to know specifically about which Et we are interested in. Now it is very interesting to think of these representations to be some sort of a gateway towards a better understanding of the stress components. So what I mean to say is that suppose we have taken this kind of a very general plane which is lying obliquely to all the coordinate axes, But suppose we chose this plane to be perpendicular to the x1 axis, then surely the unit outward normal to it would be along the E1 vector, that is along the x1 direction. I repeat, suppose we had chosen this plane not to be lying along this some arbitrary direction, rather it was a plane which was parallel to the x2 x3 plane, or equivalently perpendicular to the x1 axis. In that case, the n hat would be nothing but the E1 vector. The E1 hat is the unit outward, is the unit normal along the x1 direction. Then you see what happens. Then this normal component of the traction vector, what does it become? You put E1 here, you put E1 here. Okay, then what really happens? So you can do this little exercise. Actually, it's very interesting. So suppose n hat is equivalent to E1 hat. Okay, and what is E1 hat? The equivalent matrix representation of it. So we can of course write it with a bracket here, but what I mean to say is that what are the actual components of it in matrix form. So we have to write it like a column matrix, and that column matrix is going to have three components. The first component is going to be 1, the second component is going to be 0, and the third component is going to be 0. Similarly, if you had taken this to be the E2 hat, it would have been 0, 1, 0, and the E3 hat would have been 0, 0, 1. Now we are only concerned about E1 hat. In that case, okay, in that case, what would be our Tn? It would be, so if we use this formula, it would be E1 hat transpose sigma E1 hat. And what is that? It's very simple. Well, you just write it. So this is the transpose, so I have to from a column matrix I have to make it to a row matrix. So it becomes like this. The sigma matrix is sigma 1 2, sigma 1 3, sigma 1 2 again, sigma 2 2, sigma 2 3, sigma 1 3, sigma 2 3 again, and sigma 3 3. So I'm writing this out in detail just for the ease of your understanding. Every time you do not have to write the whole thing. So if you do the actual multiplication, what it will come out to be is just this. You can check for yourself. Okay, you can actually check for yourself. So and this gives us a clue actually about the physical interpretation, or the geometrical interpretation of the various components of the stress. So see, the sigma 1 1, from this what we are concluding is that the sigma 1 1 is nothing but the normal component of the traction vector on a plane which is perpendicular to the x1 axis. It's as simple as that. You actually know all of this stuff from your first year mechanics. Now what about the sigma 1 2? You see there are two different indices here. So of course we cannot be using this normal component, and you know that this is the shear component. So for that shear component, what you have to do is you can think of a generic shear component, not necessarily this particular shear component. So what you can do is you can consider a let me go to the next slide. So to interpret sigma 1 2, let's say only sigma 1 2, you can take the normal component to be the E1, so that you will have the equivalent matrix representation as 1 0 0, and the ET hat. Okay, mind you, I am no longer taking the ES hat, I am taking the ET hat. That will be E2 hat, and that will be 0 1 0. Okay, so what I am doing is, instead of this this generic T or the specific TS, I am taking the a general shear component of the traction vector. So I can actually make a note here that that will be nothing but where, if we go back to the previous slide, you understand that the ET hat, it lies along the plane, but it is different from ES. That is all there is to it. Okay, so this is some general shear component. So coming back to this interpretation of sigma 1 2, if you take the n hat along E1 and the ET hat along the E2, which is the 0 1 0, then what you will obtain for the shear component TT, that is n hat transpose sigma ET hat, and that will be nothing but E1 transpose sigma E2. Alright, so from here you will end up with this is equal to sigma 1 2. Okay, so you do it the other way around, you will end up with again sigma 1 2, because this stress tensor is actually symmetric. So it's a little fun exercise to do these little calculations and convince yourself that what you are expecting it to be true mathematically, from your actual calculation also it comes out to be true. Alright, so you can go about doing all these little fun things, but as far as the topic is concerned, we have completed it, and in the next part of the lecture, what we'll do is we will utilize the concepts that we have developed here, particularly in connection with the normal component of the traction vector, to develop our ideas towards the calculation of the extremely important topic of principal stresses. So we are building it step by step. So first we discussed generally about traction, then we talked about stress components. In this part of the lecture we talked about the normal and the shear components of traction, and then we are going to build on the normal component of the traction vector towards the idea of principal stresses, and you'll see the similarities and some differences with the idea of principal strains that we studied in the previous chapter. Alright, thank you very much.